Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 4th, 2025, about 6 days ago. It makes a bold claim that no algorithmic process, in other words, nothing that a Turing-style computer can compute, can ever achieve artificial general intelligence as long as we define that as truly creating new functional capabilities rather than remixing what was already there. The paper is titled, On the Computability of Artificial General Intelligence. And, as we will see later, the implications for how we think about future artificial intelligence systems are quite profound. Alright, after that bold claim, Figure 1 lays out what true artificial general intelligence would need to do. The left box represents a mechanism that, given some input X, must generate a brand new function that was not in its toolbox before. The middle block shows this new function producing an output Y. The right panel depicts the existing set of functionalities, into which the new function is then inserted so it becomes part of the system's future capabilities. So while Figure 1 sketched what a creative system would need to do, Figure 2 drops right down to the simplest possible component, a single wire. The top diagram shows an input signal, flowing unchanged along the wire to become the output. The equation states that the wire function returns A, which means the output always equals the input. The truth table underneath lists the two possible digital values, 0 and 1, and confirms that both simply pass straight through. So while Figure 2 focused on a single wire, Figure 3 introduces the basic, non-trivial building block, the NAND gate. The top diagram shows two inputs, A and B, feeding into the gate, whose output is the function f sub NAND. The middle line states that f sub NAND of A and B is the negation of A and B, so it only outputs 0 when both inputs are 1. The truth table underneath lists all four input pairs and confirms that behavior row by row. Alright, while Figure 3 isolated a bare NAND gate, Figure 4 embeds a single NAND gate inside a larger circuit box. The left side shows an n-bit input vector, labeled x1 through xn, feeding into that box. Near the top, one pair of those inputs enters the single NAND gate, whose output line becomes y1. The remaining input lines pass straight through the box to become outputs y2 through ym, so the whole circuit still only performs one non-trivial NAND operation. So while Figure 4 showed a single NAND gate inside a circuit, Figure 5 presents a full K-gate candidate for a minimum artificial general intelligence system. The whole diagram depicts n-bit inputs entering on the left, flowing through several interconnected NAND gates, and emerging as m-bit outputs on the right. The left block shows the input side of the circuit that transforms the incoming bits. The right block shows the output side that produces the final vector. The narrow middle section indicates that this entire construction is treated as one minimal algorithm fk of x that supposedly yields y. Well, while Figure 5 treated the K-gate circuit as one block, Figure 6 shows how that circuit can always be split into two pieces. The left group of NAND gates represents the full K-gate system that maps the input vector x to the output vector y. The right side rewrites this as a k-1 gate subcircuit that maps x to an intermediate vector z, followed by a single gate that maps z to y. This decomposition is crucial, because any supposed minimal creative circuit must still break into simpler non-creative parts. So the core message is stark. If creativity means generating genuinely new functional capabilities, then no finite algorithm, no matter how large, can ever reach artificial general intelligence in that strong sense. The results suggest future systems will excel at powerful recombination, not true invention, and they nudge questions about human minds toward non-algorithmic explanations. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.